Right, well, thanks for everything we've had here. It's been a great time. I think I'm looking forward to going up ski lift tomorrow. Is it tomorrow? Yes, tomorrow. Last time I saw a broken ski lift was in Vienna, when we had the Mixed Mode conference there some years ago. And so we're back in a skiing place, so I thought I would talk about Mode 2 and Mixed Mode as being appropriate. And I think I'll introduce it by a problem we had, really, a failure, I guess, or a failure to do the tests in the lab and get Mode 2 crack growth. In fact, quite a lot of people over the years have tried Mode 2 cracking by all sorts of different specimen geometries and techniques, and a lot of people have tried, and very few have succeeded. And this is a case where we failed. Aoki Otsuka in Japan has done a lot of work over his lifetime in this, and he seems to have remarkable success. So we tried to repeat one of his tests. Essentially, we had a tubular sample in a tension torsion machine, and we put in an axial crack, and under cyclic torsion, of course, that sees pure shear, and the Mode 2 crack should extend along these blue directions quite nicely. Very often, though, we find with pure torsion that the cracks will bifurcate on these red plates and grow in Mode 1 instead. Otsuka had the marvellous idea that you could put on a compression, a steady compression, to close those incipient cracks, and then they would grow. And that would stabilise the Mode 2, and we could do some nice Mode 2 experiments. So we got our specimens ready, got the machine going, and however large a compressor stress we put on, the cracks always grew in the red direction as Mode 1, and we failed completely. Otsuka in Japan, he used asymmetric 4-point bending and some clamps on to put in the compression, and he got some nice Mode 2 stable shear crack growth. But apparently the same test, with different specimen geometries. Why did we fail when we succeeded? That's really what this talk's about. Only one other point I ought to mention. We couldn't really pre-crack our samples, couldn't think of a way of doing it. The cracks are put in by spark erosion with a small wire, and so in our case we have a root radius of curvature of 0.08 at the end of the notch, that's what to call it. But Otsuka, I think he pre-cracked his samples, and I guess they were a bit sharper. Let's move on. Cracks do grow in Mode 2 in practice, of course. Even if you can't do it in the lab, they do in real life. This is an example that I use quite often. You may have seen it before. After a railway line, top surface here is the rolling surface. We've got a travelling rolling contact fatigue, and we get cracks in the railway line. And where you see the cracks going along here, a fairly shallow angle to the surface. That turns out to be a plane that's under high shear stress, cyclic shear, so it's a shear mode crack. And if you live in a country with high-speed trains and a temperate climate, where it rains, so you get a bit of fluid around, then those cracks grow quite happily. No point in trying to grow them in Arizona, because it's too dry, there's no fluid, and instead you get cracks going across the line, like this one, which then lead to a fracture. This, and the branches upwards, will be the Mode 1 type of crack. Another example that you'll be much more familiar with probably is just torsional low cycle and high cycle fatigue. It's a fatigue curve. These cracks sketched are real ones taken off the samples that this research student was looking at. In high cycle fatigue, with a crack initiated shear, it transfers into a Mode 1 like we had on the previous slide. In low cycle fatigue, you get much more shear mode cracking. So shear mode is quite possible to have in real life. Why do we have our problems? Well, this analysis I hope will explain where I got it wrong, because I believe fraction mechanics basically. So, we've had at least two people have mentioned the Ingalls solution, or the Savin solution. We've set that up on a spreadsheet so I could solve it. It's purely an elastic solution for stresses around an elliptical notch, which I have exaggerated here to make the notch narrow. It's very crack-like. And also we can control the radius of curvature of the crack tip, because all real cracks are blunt. There's no such thing as a singular crack. A singular crack can only be found in the mind of a mathematician. In real life, that, aren't I? In real life, if a crack exists, it's got to be at least 2 or 3 atomic dimensions wide at the crack tip. Otherwise, if you get to 1 atomic dimension wide, you've really just got a dislocation. Less than that, the crack isn't there at all. So there must be at least a finite radius of curvature here. To load this, we can apply stresses S and also lambda S at any angle alpha, so I have a completely general biaxial loading field that I can analyse through the Ingles method. This line here with the red points is just a vector taken from the root of the notch, and we can examine stresses along that vector at an angle phi to the horizontal and see what the stress field looks like. I'll start with mode 1 just to get you going and understanding what we're doing. All the graphs that follow look like this. In terms of the axes, they're normalized axes. Logarithmic scale horizontally, which is distance from the crack tip divided by the radius of curvature. Rho, sorry about my lack of ability at getting to there you go. I did this in a hurry. So T over rho is just normalized, and when it's 1, of course, that's saying just 1 radius of curvature away from the crack tip. So that's really quite close to the crack tip there. Vertically, the stresses, I've got sigma x, sigma y, tor xy, Cartesian axes, y is normal to the crack and so on, and they're all plotted here. And then we normalise by kts, where kt is this formula. So when you get to the crack tip, of course, mode 1 stress gets to unity, which you see up here at the top left-hand corner. The dotted line is the fraction mechanics solution. It's the usual result that goes off to infinity when you get to the crack tip, which is point a bit easier. In this case, and sigma y are exactly the same line. One of the problems with the Westergaard solution, it says sigma x and sigma y are equal. If we are on a line straight ahead of the crack, and if you bother to even titles, yeah, phi is 0, so we're looking at the line straight ahead of the crack. In our solution here, though, we find that the sigma x, which is green, is completely different to the red line, except over here, and this is where LEFM is valid. And we get breakdown of linear elastic fraction mechanics formally about here at a ratio T over rho about 10. So if you get too close to the crack tip, this is where I went wrong really. I was always taught that the fraction mechanics is marvellous the closer you were to the crack tip. But in fact, with a blunt crack, with a real radius of curvature, that's no longer true. And we find that essentially from there onwards, tor xy, which here is 0, and sigma xy can be quite different, and neither of them go to infinity. They both go to 0 at the crack tip, which they must be. You can't have a stress normal to a free surface, and certainly not an infinite stress. So fraction mechanics is slightly out, suggesting infinite is a good approximation to 0. I've gone on too many. Sorry, there we are. This is the same thing, mode 1, but phi equals 45 degrees. So that's a bit more fun because we now see all the stresses appearing separately. 3 fraction mechanics lines are there. Again, beyond or above 10 for T over rho, fraction mechanics works very well, which it should. But as we go down towards the crack tip itself, we find that we get very different results. We even find stresses changing sign, and that's why I've used a linear scale here rather than logarithmic. Logarithmic scales are great because all this stuff is hidden, which is where all the problems are. You can't see it. This is mode 2, which is the point of the talk really. Phi equals 0, so it's straight ahead of the crack, and we find there's a shear stress here. Sigma x and sigma y are both 0 on the horizontal axis. And again, we have our fraction mechanics result, which is giving quite a different answer. I should practice a bit about dimensions and so on. I'll put down here my chosen crack shape. That's the length of the crack, or the half length of the ellipse, and the height. So it's 10,000 to 1 ratio, so it's very crack-like. And in this case, the radius of curvature would be 10 to the minus 7 millimeters, or 1 angstrom. But with this normalization scheme, it doesn't really matter what dimensions you take. If I change B and rho, therefore, you'll find you get exactly the same curves because it's normalised here. And normalised with respect to KT, which is just this formula. And so the curves are invariant with respect to life stress, with respect to radiative curvature, and indeed with respect to T-stress, which is quite interesting. Well, actually this tells you why the Sheffield tests failed. So we should have actually thought more about this picture. The idea in mode 2 was to suppress the mode 1 cracks. Mode 2 crack will initiate at the notch root, which is over here. And guess what? There's no shear stress. And there's no sigma x, there's no sigma y. All components of the stress tensor are 0, and I'm trying to grow a crack in an area where there's absolutely no stress. Why did I fail? Well, I should have thought of that earlier before we started the test, but there we go. I could end the talk there. Only, what about Aoki Otsuka? He shouldn't have succeeded, according to this theory. So there must be a bit more to it. And this bit took me quite a long time to understand. We got these curves, quite a few years ago we were working on them. It's only had a shower one morning, like a year or so ago, that I tumbled to what was wrong, sort of the process zones. Probably the process zone, I've just done another mode 2 picture, phi equals 45 degrees, so now you can see the other stresses appearing. And again, this is an invariant picture for mode 2. In fact, there are only two fundamental pictures, one for shear mode and one for tensile mode, which we had earlier. And those two pictures describe all the stress fields that you get for biaxial loading for any combination. Process zone. A few people have mentioned process zone already, and I never really quite understood process zone. I've always been a fan of plastic zones and things related to that. But when you think that this dimension here, defined by rho, the radiative curvature, that's tiny. And so to say the process zone is this small would be nonsense in terms of plastic zones. This value of rho is of the order of the crack growth increment per cycle. It's tiny, and the plastic zone is much, much bigger. So I still believe very much plastic zones or high strain zones or something like that are process zones for deformation, for the cyclic deformation that drives a crack. What I told you in the chart was that there were two process zones. Why should there be only one? First paper I wrote, I think it was years ago, was basically saying there are two parameters, effectively two processes going on. And now I'm just retired and realise that perhaps if there are two processes, they've got the zone each. It's taken me a long time to get there, but there we go. So this is the fatigue failure process zone, which is where the failure process is occurring. The decohesion, if you like, Tompkins model, which I do, or tearing of atoms apart, and all sorts of ideas that come up in the last 2 days, which are actually involved with the failure rather than with the deformation. And so this process zone is rather small. I've sketched on two of them here. The figure is exactly the same as we had 2 ago for mode 2. This is the Sheffield case here. The process zone from the crack tip was presumably finite, but it wasn't big enough to get into a region where there's any significant stress. If you've got no stress intensity, or no intensity of stress, let's say, then nothing happens. And when I go to the Otsuka test, in her case, the process zone is often bigger, and therefore it includes these big stresses here, and therefore there's a good intensity of stress in the crack growth and shear. The main difference between this and this is the value of rho. I said on my second slide that rho was 0.08 millimeters in the Sheffield tests, which makes our process zone on this normalised scale rather small, and too small to grow a crack. So I believe in blunt cracks. Other people do, I gather, from discussions up to now, but in this case the crack is too blunt to allow the crack to grow in mode 2. If we have a rather sharper crack, with still a finite radius of the crack tip, then we can actually develop a stress intensity and a decent driving force. I've just got time to mention this really. We'll explain now Otsuka and the Sheffield tests, I hope. I just pop this in as the last one in case you're interested in this method of plotting results. This is actually back to mode 1 again. Stress is ahead of the crack tip. I've actually done 1, 2, 3, 4 and 5 different radii curvature, and they all follow exactly the same line on this normalised plot, except when you get to the far field. That's actually a circular hole rather than a crack, which surprisingly even fits the line here. And then we have sharper and sharper notches, as a 10 each time. But in the far field, of course, you get different results. And these relate to KT for each. But they all come to this line. The sigma x in green has to come down to 0. The one thing I've changed here is I've made it logarithmic on this axis. So it's more like the normal plots we see. We expect LEFM to give you a nice straight line of slope half, minus half, and there it is. The other thing I've done is I've added a 0.25 onto t over rho. And I've done that on purpose just to make this end of the curve straight. Originally it went across to 1 and went off to infinity in that direction. But by putting in a little correction factor there, sorry, a little fudge factor there, we can make the line straight. And if you remember Paris and Krieger, which came up earlier today, they put in a factor much like that, only theirs was 0.50 rather than 0.25. So if we want to use this method of Ingalls or Savin to get the crack tip stress fields very close to the crack, this is a way you can actually do it mathematically without writing out all the formulae that Savin produced, which I think would get the record today for the length of formulae. I had none today in my talk, which is unusual. But there we go. I've run out of time, really, haven't I? Conclusions are there on limits of fracture mechanics, which are important. I've not mentioned the one at the top end. 0.1d comes up quite a lot. Perhaps to be more accurate, make it 0.01, depending on what errors you require, is also a lower limit. However, I could reduce all these conclusions into one, if you like, courtesy of apologies to William Shakespeare. We're looking at a mode 2 crack. We need to examine the crack tip stress field. Is the crack too blunt or not too blunt?
Thanks very much indeed, Mike. Very early. Thank you. Right, questions, Paul?
Thank you, Mike. So would you have been successful if you had been growing a crack at larger cyclic loads, where your capacity zone would have been bigger?
We took the compressive stress all the way up to yield.
But
we still didn't manage to
the cyclic torsion, if you put on bigger
I think
delta,
it's unlikely we would have probably got faster mode 1 cracking, really, in that case, because a notch is just a notch, it's too blunt.
Yeah, but you would have pushed it out into that region where the stresses are more well behaved.
By increasing T, yes, yeah. Maybe, but I think probably sharpening the crack would have been a better idea if you could have thought of a way of doing it.
Sylvie.
Are you sure you are really in shear? Because if you put only one crack like this, and you have your boundary condition, I'm not sure you keep the shear on the suitable plane.
Well, certainly for a tubular cycling torsion, that is a shear plane.
Yes.
So without the crack there, it's a nice case of reverse shear. We're just putting the crack on what should be a shear direction. And certainly in low cycle fatigue, we do get nice shear cracking in that direction. To be fair, in low cycle fatigue, it's usually a three-dimensional crack. It's also got mode 3 around to help stabilize things. I would say yes. It was a shear crack from having done torsion for the past 21 years.
Actually, may I ask for a shape of this was tubular?
See, it's just straightforward tube, fairly thin walled.
Thin?
Fairly thin, yeah.
Very thin?
And then you put the crack
through
through
the
thickness.
through the crack.
That's right. I mean, if it's any help, we also did crucible
Well,
stress tests
may I ask?
with angle cracks, and those grew in shear very nicely with the right loading pattern. So we can get shear crack growth in that rail steel with the right loading.
But if you apply this kind of, compressive stress,
Yes.
crack like that.
Yeah.
So you have something as a Brazilian nut. So actually, if you apply the stress like this, you apply actually some mode 1 to the crack tip as a nut.
You would get a small mode 1 in tension equal to the T-stress, effectively, that you're applying parallel to.
No. Compressive stress.
That's right, compressive stress. Yeah.
Compressive, you apply, if you crank, it's like this,
Yeah.
and you apply this compressive stress. So you apply actually the mode 1
Yeah. Across the
like there.
Yeah.
So actually you have a mode 1 price.
But no, but that is
It's
static.
only a static.
That is a static load. It's not a
No,
cyclic.
it's but mode 1
It's a mean stress.
Mean stress.
Yeah. Yeah.
Okay, any other questions for Professor Brown? Anything else?
Mike, do you want to expand a bit why you made that comment about it being the bearings in two as well?
That's observed by looking at the results. It's quite, I found that quite an interesting comment. I expected to see a T variation. I can explain why, I believe. If I go back to this picture, which has rather expanded scales, I would see a variation of T down here.
Okay.
Okay. But when I'm very close to the crack tip,
Now you want
essentially
to,
because of the shape of the crack tip, the notch of that shields you from the influence of the T-stress. But more importantly, with these particular dimensions, my stress concentration factor is 20,001. Rather big. So if I put in a T-stress, I've got to go up to a factor of 20,000 to get up to here, times that. So I suppose it is there, but you just can't see it, it's minute. You would only see it really with, for example, a circular notch, which is really what we're looking at.
Thank you. Please.
When you perform a similar test and you twist the crack by 90 degrees, does you observe a similar behavior?
So it's
When you take it, twist it by 90 degrees and make again the torsion, then you have again a mode 2?
Well, we didn't have to do that because we wanted to put on the static compression and therefore it had to be an axial
Then you
crack.
have no problem.
So we didn't choose to do that. But I'm sure if we did that, we would get the same result, unless, of course, we could make a very sharp crack. The example where you see that working well is in my picture of torsion, the normal cycle fatigue torsion curve at the beginning. And that will give you either circumferential cracks or axial cracks, you get both.
The Japanese paper which you have cited, they get this pure mode 2 crack growth only under compression load or without compression?
As I skated over that a bit, if you're going to look at steels, then you found you needed to put this compression load on. Much of Otsuka's early works on aluminium alloys, and then the compressive load wasn't needed. For some reason, because of the characteristics of the steel, we found that they're more likely to branch, and therefore we had to put on these clamps to stabilise the growth.
Okay, shall we wind it up there and thank Mike again for a very urbane talk? Thank you.